diving into the world of cleaner energy with you all again today, but we're not just focusing on the usual suspects like solar and wind.
Right.
We're talking about making the,
Yeah.
let's call it the necessary evil, a little less evil,
Okay.
at least until those renewable grids are fully up and running.
Yeah.
And by necessary evil, we're talking about coal.
Exactly. Projections show coal sticking around until at least 2050.
Wow.
So anything we can do to minimize its environmental impact is going to be crucial in the coming years.
Absolutely. And one of the peskiest problems with coal power, this byproduct we call FGDW, flue gas desulfurization wastewater.
Yeah.
You've probably heard about it, I'm sure many of our listeners have. It's loaded with heavy metals like mercury, nickel, and chromium.
And a lot of other elements, too.
Oh, really?
High concentrations of calcium, magnesium, all those add up to a real headache when it comes to treatment and disposal.
Right. Those traditional treatment methods, they're not perfect.
Yeah.
So this research paper we're looking at today, published in RSC Advances, really caught my eye.
Okay.
They're proposing a solution using ion exchange resins to tackle that heavy metal load in FGDW. And what's interesting here is the potential for not just removing those metals, but actually recovering them.
It's a fascinating approach. And yeah, they're not kidding. These resins are not your average filters.
Okay.
They're highly engineered to target specific ions.
Okay, so before we get into the specifics of these resins, can you give us a quick rundown of the key culprits in FGDW? What did these researchers actually find in their analysis?
Absolutely. And the paper actually breaks it down really well in Table 2. As we mentioned, mercury, nickel, and chromium are obviously the heavy hitters, the ones they were really focused on, but they also found significant levels of calcium, magnesium, and other elements that influence how effective any treatment method will be.
So it's like a heavy metal cocktail with each ingredient potentially interacting with the others.
Exact.
No wonder those traditional treatments have their limitations.
Exactly. Conventional methods often involve coagulation and precipitation, which is basically just trying to force those metals out of the water and into a sludge.
Which then needs to be dealt with.
Exactly.
Safely disposed of, which adds another layer of complexity and cost.
Precisely. And that's where these ion exchange resins come in.
Yeah.
They offer this unique combination of efficiency and selectivity that traditional methods just can't match.
Okay, so let's talk about these ion exchange resins. What are they, and how do they work their magic on this heavy metal soup? So these ion exchange resins, they're not just some generic filter, right?
Right.
The researchers specifically chose two types for this study, Curelite S930 and S920.
Yeah.
What makes them so special in the world of heavy metal cleanup?
Well, what's so fascinating about them is that each resin is engineered with a very specific appetite for different metals, and that all comes down to their chemical structure.
Like molecular gourmands, each with their preferred dish.
Exactly. Purolite S930, for example, that's our generalist.
Oh, and
Think of it as having tiny little claws,
okay.
these immunodiacetic groups, and they can grab onto a variety of positively charged metal ions.
Yeah.
Nickel, chromium, copper, zinc. It's not particularly picky, but very effective at removing those common culprits.
So it casts a wide net, so to speak.
Exactly.
What about S920? It sounds like it might be our mercury specialist.
You are right on the money. S920 is all about mercury.
Okay.
It has these isotheronium groups
Right.
that create this remarkably strong bond with mercury ions.
Wow.
Almost like a magnet specifically designed to pull it out of the mix.
I'm picturing it now. Mercury doesn't stand a chance.
Nope.
But what I find really intriguing is that the researchers didn't just test these resins in isolation.
Right.
They designed a whole pilot study to see how they'd perform together in a real-world scenario.
Absolutely. They created like a miniature wastewater treatment plant,
Wow.
complete with tanks, filters, and of course columns filled with our resin heroes.
A mini metal-removing factory.
Exactly.
So can you walk us through how they put this pilot plant to the test with this FGDW?
Sure. So it starts with collecting the FGDW, and they actually give it a bit of a pre-treatment filtration to get rid of any large particles, and then an activated carbon filter to deal with some of the bigger organic molecules that might interfere with the resins.
So this is all about prepping the wastewater for its close-up with the resin.
Exactly. Then the pre-treated FGDW is pumped through not one, but 3 ion exchange columns, each with a specific resin inside.
Okay, so I'm assuming those columns are strategically arranged.
You bet. 2 columns are filled with our generalist S930,
Okay.
followed by a final column of our mercury specialist S920.
Okay.
So it's like a 1-2 punch, but with a final knockout blow specifically designed for mercury.
I like it. So S930 takes care of the bulk of the heavy metals, and then S920 acts as that final line of defense, making sure that anything that slips through gets captured.
Exactly.
How do you actually measure what's happening inside these columns? How do you know how effectively each of these metals is being removed?
That's where this concept of breakthrough curves comes in.
Okay, I'm intrigued. How do musical chairs relate to heavy metal cleanup?
Okay, so think of the resin beads as chairs and the metal ions in the wastewater as people who want to sit down.
Okay,
As the wastewater flows through the column, those metal ions are trying to grab onto the resin.
yeah,
If they find a spot, they're removed from the water.
makes sense.
But once all the resin seats are full,
Yeah,
any new metal ions, they just flow straight through.
interesting.
That's the breakthrough.
So the breakthrough curve is basically a visual representation of how quickly those resin seats are filling up.
Precisely, it shows you how much of each metal that resin can hold before it becomes saturated and how different metals might compete with each other for those spots.
That's a really clever way to visualize it.
Yeah.
So what did these breakthrough curves reveal? Were the resins up to the task? Did they pass the heavy metal challenge? So the suspense is killing me. Were the resins up to the task? Did they pass the heavy metal challenge?
They did. The results were really impressive.
Okay.
Table 7 in the paper shows near complete removal of nickel, mercury, and chromium.
Wow.
We're talking 100% completely below detection limits.
That's incredible. And remember how we were talking about all those competing ions in the mix?
Right.
Especially the high levels of calcium and magnesium?
Yeah.
Sounds like the resins weren't too bothered by them.
Not at all. Both calcium and magnesium showed very low affinity for the resins. They basically just passed right through the columns without really interacting.
Interesting. And aluminum was the same way, right?
Yeah, aluminum barely touched by either resin.
So they specifically pointed that out, that aluminum wasn't being removed.
Right.
Is that a problem, or could that even be advantageous in some cases?
That's a great question, and in this case, it actually highlights one of the strengths of using these resins, their selectivity.
Nope.
They're not just indiscriminately grabbing onto anything with a positive charge.
Right.
They're attuned to target those priority heavy metals, nickel, mercury, chromium,
Yeah.
while letting other elements pass through.
It's a feature, not a bug.
Exactly. You're designing for specific outcomes.
What about the other metals they tracked, like iron and manganese? What did their breakthrough curves tell us about them?
Now, those are where things get interesting.
Okay.
Initially, both iron and manganese showed some removal by the S930,
Okay.
but as more wastewater flowed through, they were actually released back into solution.
So they were binding to the resin and then getting kicked off.
Exactly.
What's going on there?
It's all about competition for those resin seats we talked about.
Right.
Other metals, like nickel and chromium, they have a much stronger affinity for that S930 resin.
Yeah.
So as those higher affinity metals flow through, they displace the iron and manganese that were initially bound.
Wow. So it's like this dynamic system with different metals constantly vying for those prime spots on the resin. Looking at the breakthrough curves for that first S930 column K1, were there any other notable observations?
Well, as we said, calcium and magnesium cruised right through completely unaffected aluminum, and manganese had their brief moment of binding before being displaced.
Right.
Iron, however, showed a bit more staying power, indicating pretty effective removal for a significant period.
But eventually, even iron felt the pressure from those higher affinity metals.
Exactly.
What about nickel and chromium? They were our all-stars in the S930 columns, right?
Nickel in particular showed a really strong affinity for the S930,
Yeah.
consistent removal over an impressive time frame.
Yep.
Chromium removal was also robust initially, but then we saw this gradual decrease in its efficiency, which again suggests that something else was starting to outcompete it as more wastewater flowed through.
Which brings us to our mercury specialist, S920, waiting in that final column.
Right.
Was it able to capture the mercury that the S970 might have missed?
It performed beautifully. You'll recall that mercury wasn't removed as effectively by the S930.
Right.
However, that S920, with its specialized isotheronium groups, it captured virtually all of the mercury,
Amazing.
further proving its role as this targeted solution for this particularly toxic heavy metal.
That targeted approach is remarkable.
Yeah.
You did notice in the data, though, that the S920 also picked up some nickel and chromium. I thought those were supposed to be the S930's domain.
Right, but that's where this multi-column system really shines, because
Yeah.
the S920 has such a high affinity for mercury, and its concentration is relatively low. It's not operating at full capacity, which means it can still grab any residual nickel or chromium that makes it through those S930 columns.
So it's acting like a final polishing step.
Exactly.
Wow, so we've successfully captured our target heavy metals,
Right.
but they're stuck to the resin beads.
Right.
How do we get them out and ideally put those metals back to good use?
That's the next stage of the process solution.
Okay.
By using a strong acid, you can actually strip the metals from those resin beads and collect them in a concentrated solution.
Okay.
And here's where it gets even more intriguing, those elution profiles you mentioned earlier.
Right, it's not just a jumbled mess of metals coming out, is it?
Not at all. The elution profiles shown in figures 8 and 9 reveal that by carefully controlling the acid concentration and the flow rate,
Okay.
you can actually separate the metals as they're eluted from the resin.
So each metal has its own elution personality, so to speak, coming out at a slightly different time.
Precisely. And what's particularly promising is the potential for recovering specific metals like nickel in a relatively pure form, ready to be recycled or reused.
And that's what I call closing the loop.
Right.
Instead of just removing a problem, we're recovering valuable resources. This research does more than just explore a new technique.
Right.
It hints at a fundamental shift in how we approach wastewater treatment in general.
Absolutely. This study provides a glimpse into a future where wastewater isn't just a waste product, but a potential source of valuable materials.
Moving from that linear take, make, dispose model to something more circular and sustainable.
Exactly. And this research really highlights how these targeted technologies like ion exchange resins, combined with clever design and a really deep understanding of the chemistry involved, can help us unlock that potential.
It really makes you wonder what other hidden sources of valuable materials we might be overlooking. Could this approach be applied to other industries grappling with heavy metal contamination? Maybe even tackling that growing challenge of electronic waste. Food for thought. This has been an incredible deep dive. Thanks for walking us through it.
It's been my pleasure.